Hello and namaste to all of you. This is Name-Shalu Singh from Department of Physiotherapy and Diagnostics from Jayoti Vidyapeeth Women's University. For today's topic, I'll be discussing with you about viscosity. Let's see what does viscosity means or what is its definition. So, viscosity is defined as the measure of resistance of a fluid to gradual deformation by shear or tensile strength. And in other words, viscosity describes a fluid's resistance to flow. Simply put, we can say that honey is thicker than water, right? So, in turn, honey is more viscous than water. So, a definition of viscosity can also be said as that viscosity of a fluid is a measure of its resistance to deformation at a given rate. And for example, that syrup has a higher viscosity than water. Now, let's see how we calculate viscosity. Viscosity is measured in terms of a ratio of shearing stress to the velocity gradient in a fluid. So, if a sphere is dropped into a fluid, and viscosity can be determined using the formula neta 2 Ga 2 delta psi 9V. Okay, so psi is the density difference between fluid and sphere tested. Alpha is the radius of this. A is A or alpha, which is the radius of the sphere. G is the acceleration to the gravity, and V is where the velocity of the sphere. And other V is distance traveled by sphere per time it takes to travel the distance. So viscosity is measured in Pascal seconds. So the SI unit is your Pascal seconds. So as you can see in that if you write the equation and if the speed of the sphere is less, the viscosity will be more, and thus the more viscous a fluid is, the more resistance it offers to any object moving inside it. So although all liquids they have a certain value of viscosity, therefore the liquids is generally considered as high or low, and keeping the viscosity of water as the benchmark. So, for example, the viscosity of water is 0.001 Pascal seconds. Then that of the air is 0.000019 Pascal seconds, and that of motor oil is 1. So, you can pretty much do the math here that also the viscosity of liquids they decrease as the temperature increases, while for gases it increases with the increase in your temperature. So now further carrying on here is that for viscosity there is this thing which I'll tell you what is the need to measure viscosity. So or why should you measure viscosity? So gathering the data of a viscosity of a given material, it will help manufacturers to predict how material behaves in the real world. For example, if the toothpaste does not have correct viscosity, or if it will either be too difficult to pump out of the paste, or too much of it will be pumped out. So also knowing the viscosity of a material affects how production and transportation processes are designed. So there are basically two types of viscosity. So viscosity is a measure of friction of fluids, and there are two ways to measure a fluid's viscosity. First of all is dynamic viscosity or absolute viscosity, and second is your kinematic viscosity. So many are confused between two viscosities, measures and consider them to be one and same, but in reality they have significant differences between them. And there are a few applications of kinematic viscosity which make it more useful than absolute or dynamic viscosity. So Also, the unit of kinematic viscosity is strokes, named by the British physicist Sir George Gabriel Stokes, and a stroke is defined as 1 centimeter squared per second. Okay, so further in details about viscosity. So, in simpler words, that viscosity is the resistance of a fluid, liquid, or a gas to change its in shape or a movement of neighboring portions relative to one another. And viscosity denotes the opposition of a fluid, and also that the reciprocal of viscosity is called as fluidity. So these are vice versa of each other. So fluidity is a measure of ease of flow. Also, molasses, for example, it has a greater viscosity than water. So because a part of fluid that is forced to move carries along to some extent adjacent parts. So viscosity may be thought of as an internal friction between the molecules, and such friction it opposes the development of velocity differences within a fluid. And viscosity is a major factor in determining the forces that must be overcome when fluids are used in lubrication and transported in a pipeline. So it basically controls the liquid flow in such processes as spring injection, molding, and surface coating. Now, for example, many fluids, the tangential or shearing stress that causes that flow is directly proportional to the rate of shear strain or the rate of deformation that results. So, in other words, the shear stress is divided by the rate of shear strain and is constant for a given fluid at a fixed temperature. And this constant is called as dynamic or absolute viscosity, and also known as viscosity. So fluids, they behave in a way that are called as Newtonian fluids in honor of Sir Isaac Newton, who first formulated the mathematical description of viscosity. So as I've already told, that dynamic viscosity is force into time divided by your area, and the unit is your Pascal seconds. So now uh, this viscosity is let's see what are the factors affecting your viscosity. So viscosity is first and foremost a function of a material. So the viscosity of water at 20 degrees Celsius is 1.0020 millipascal seconds, so which is conveniently close to 1 by coincidence. So most ordinary liquids have a viscosity on the order of 1 to 1000 millipascal seconds. So while gases have viscosity on the order of 1 to 10 micropascals seconds. So pastels, gels, emulsions, and other complex liquids, they are harder to summarize. And some fats like butter or margarine, they are so viscous that they seem more like soft solids than like flowing fluids. And molten glasses is extremely viscous and it approaches infinite viscosity as it solidifies. And since the process is not as well defined as true freezing, some believe that glass may still flow even after it has completely cooled. But this is not the case. At ordinary temperature, gases are solid as like true solids. And from everyday experience, it should be common knowledge that viscosity varies with temperature. Honey and syrup, they are made to flow more readily when heated. Engine oil, hydraulic fluids, they get thickened and appreciably on your cool days, and significantly they affect the performance of your cars or vehicles and other machineries during the winter months. And in general, viscosity of a simple fluid, it decreases with increase in temperature. So as temperature increases, the average speed of molecules in a liquid increases, and the time amount of time they spend in contact with their near neighbors, they decreases. So thus as temperature increases, the average intermolecular force decreases, and the actual manner in which these two quantities vary is nonlinear, and they change abruptly when liquid changes phase. Now, viscosity is normally independent of pressure, but liquids under extreme pressure, they often experience an increase in viscosity. And since liquids are normally incompressible, and an increase in pressure, it doesn't really bring the molecules significantly close together. So simple models of molecular interactions, they won't work to explain this behavior. And to my knowledge, there is no generally accepted more complex models than that of those. So the liquid phase is probably the least well understood of all the phases of matter, while liquid gets runnier as they get hotter, and gases they get thicker. So viscosity of gas increases as temperature increases, and is approximately proportional to the square root of temperature. And this is due to the increase in frequency of your intermolecular collision at higher temperatures. And since most of the time the molecule in a gas, they are flying freely through the void, and anything that increases the number of times of one molecule is in contact with another will decrease the ability of molecules as a whole to engage in a coordinated movement. And the more these molecules collide with one another, the more disorganized their motion will become. So physical models, they are advanced beyond the scope of this book scope. So now newer models, they do a better job than your older models, and they also agree with the observation that viscosity of gases is roughly independent of pressure and density, and the gaseous phase is better understood than all the phases of matter. So since viscosity is so dependent on temperature, it should never be stated without it. Okay, so now motor oil, it is like every other fluid, and in that its viscosity varies with temperature and pressure. And since the conditions under which most automobiles will be operated, they can be anticipated, that the behavior of motor oil can be specified in advance. And in US organization that sets the standards for the performance of motor oil. So, in Society of Automotive Engineering, the SAE, the numbering scheme describes the behavior of motor oils under low and high temperature conditions. So, conditions that correspond with starting the operating temperature, the first number, which is always followed by the letter W for winters, and it describes the low temperature behavior of the oil at startup, while the second number, which describes high temperature behavior for the oil after engine has been running for some time. So lower the SAE numbers describes that they are meant to be used under low temperature. And oils with low SAE numbers, they are generally runnier, less viscous, and then oils with high SAE numbers, so which tends to be thicker or more viscous. So for example, 10 watt to 40 oil would have viscous no greater than 7,000 millipascals in a cold engine, and the crankcase, even if it's a temperature, should drop to minus 25 degrees Celsius on a cold winter night, and the viscosity will be no less than 2.9 millipascals in the high temperature parts of an engine near the point of overheating, which is your 150 degrees Celsius. Now, what is capillary viscometer? It is basically the mathematical expression which is describing the flow of fluids in a circular tube, and it was described by the French physician or philosophist uh, Jean puzzle. And since it was also discovered independently by German hydraulic engineer Gottlieb Hagen, it should be properly known as Hagen-Poiseuille equation, but it is usually just called Puzzle's equation. So it is written as Qm equal to pi delta P r raised to the power 4 divided by 8 neta L. Now, this was all about the viscosity. Now, you should read about it in as much detail as you can, since it was also the topic of your senior and secondary schools. So you can read it in as much details as you can. So if you have any doubts about it, you can ask me in further classes. And until then, take care and bye bye.